Now next consider the problem of cantilever beam. Now the possible ILDs are, the ILDs for reactions at A, that is vertical reaction RA, and fixed end moment MA, then shear force and bending moment at any section C at a distance A from left hand and B from right hand. Total span is L. Now here we have the reaction RA, for which we want to construct ILD, and this is bending moment at A. So now, first we will see the ILD for RA. Suppose you want to construct ILD for RA. Now the reaction is always calculated, it's a cantilever summation Fy equal to 0. If we apply condition summation Fy equal to 0, what is RA? RA is 1. So this is independent of position of unit load. Whatever is the position of unit load, RA is always equal to 1. RA is always equal to 1. Now let's take a reference line. So let's have one reference line and construct ILD for RA. Say this is ILD for RA. Write here the name of the ILD in bracket. ILD for RA. So RA is whatever is the position of unit load, RA is always 1. So that means this is constant. So ILD for RA is constant. So this is 1. This is ILD for RA. 1 on both sides. And positive since upward. So ILD for RA we have constructed. Next, let's consider MA, ILD for MA. Next, ILD for MA. And again, the sagging you take positive, hogging you take negative. See, if we take moments about A equal to 0, MA equal to, what is MA? So they due to unit load it is hogging. So 1 into X, this is minus 1 into X is the moment. Now for various positions of unit load, applicability of this equation, 0 less than equal to X less than equal to L. So at X equal to 0, what is MA? MA is 0. When unit load is at A, MA is 0. When X equal to L, MA is equal to minus L. 1 into minus L. That's all. So varies linearly. So here it is 0 and this ordinate is L. Means whatever is the best will be the ordinate. And so because this helps in plotting ILD when we use Muller-Brussel's principle. Okay, by calculation we have constructed when X is 0, when unit load is at A, MA is 0. And when unit load is at a distance X, MA is minus 1 into X. When unit load is at B, MA is minus L. So very easily we construct ILD for MA. Then next, ILD for shear force. That is SC. Let's consider ILD for shear force at section C, and the positive directions here, upward, downward, this is positive, this is the section, left downward, right upward, negative. Now again, when unit load is on AC, as usual, when unit load is on AC, what is shear force at C? So let's consider right hand part. When unit load is on left, so this is the section, left of the section, and when we consider RHS, to find what is shear force, sum of vertical forces, either on left or right side of the section. So when unit load is on the left, consider right side to find out the shear force, take sum of the vertical forces on the right of the section, and there is no force. shear force is 0. And next, when unit load is on CB. What is shear force here? Shear force, when your unit load comes here, so unit load comes here, then shear force again you consider RHS at a distance x from C, or you consider RHS, so it is downward on the right, so this is the case. So that means shear force is 1, plus 1, remember. So again, this is independent of position, so that means the shear force occurs only when, so this is the section and this is the shear force. So this is 1, this is 1, positive. So this is ideally for shear force at C. Ideally for shear force is just plus 1. But when unit load is on AC, no shear force. When unit load crosses the section C, that unit load itself becomes shear force at that section, whatever is the position of unit load on CB. So when unit load is on CB, so this is 1. So here just like a reaction is 1, but here the shear force when occurs only when unit load crosses the section C. Now next, the last ILD, let's consider ILD for bending moment. So let's consider ILD for bending moment at section C. ILD for bending moment at section C. That is MC. Again, suppose your unit, so whenever unit load is on AC, when unit load is on AC, that is left of C, so what is bending moment at C? 0, because considering a right hand side of the section when there is no load on the right, so the bending moment is 0. Now bending moment will occur only when unit load is on CB, that is crosses the section, and say this unit load now on the right at a distance x. The same load now when it comes here on the right of the section at a distance x from C, then the bending moment MC equal to minus 1 into x. X I have considered from C now. Now this is valid for A less than equal to x less than equal to L. Means at x equal to A, what is this? MC, x equal to 0, 0. This validity is 0 and B. This is 0 to B. We have considered x from C. So 0 to B. It varies from 0 to B. So when x equal to 0, so this is 0. When x equal to B, MC equal to minus B. So MC is minus B. Minus B means negative. Because this is negative, so minus. Now this is the reference line. And this is point C, here it is 0, and this is minus B. So this is B. So base is B. Whatever the base and height, they are usually same. So this is minus. So now we have completed influence line diagrams for support reactions RA and a bending moment MA. Then shear force and bending moment at any section C for a given B. Now these ILDs we have constructed, ILDs for or possible ILDs for simply supported beam and cantilever beam, we have constructed by using calculations, by establishing the relations between the structural function and position of moving unit load. So we have constructed the influence line diagrams. And one more thing, you just observe the shape of the ILDs for simply supported beam and for cantilever beam, for shear force and bending moment. See, for shear force, when the section, at any section, the shear force is a rectangle diagram or cantilever, and that is on free end side. It's a rectangle. And it's a triangle on the right of a section that is towards free end. So whatever is the best height. Similarly, say the array reaction for fixed cantilever beam is constant. See the moment, the base into height, and see the simply supported beam. If section is within simply supported beam, say you know if this is the section, the shear force diagram is this. ILD for shear, and this is if this A, this is B. This is A by L minus this is plus B by L. So left minus right side is plus, and this is the ILD for shear force for simply supported beam. And we have seen for bending, the ILD was like this, and this ordinate was AB by L. This is plus. So for bending moment, ILD for simply supported beam is this, for cantilever is this, for cantilever ILD for shear force shape is like this, for simply supported shape is like this. Why I am showing this shape? Just keep the observations for ILDs for simply supported beam and cantilever beam. This will help us while plotting ILDs directly by using Muller-Brussels principle later on, because once you are introduced with Muller-Brussels principle, then we are not going to do any calculations. So you must be in position to draw ILDs directly. Means this topic that way is very easy. Any problem of ILD, any ILD you can construct within 1 minute only. So even you have 10 minutes to solve a particular problem, but here you can complete the problem within 2 to 3 minutes by using Muller-Brussels principle. Now next, let's say Muller-Brussels principle. Say Muller-Brussels principle. Muller-Brussels principle, very important. Muller-Brussels principle. Now, see what is this principle? It's very simple. Suppose, just try to understand. Suppose we have a simply supported beam. Suppose we have a simply supported beam. Let me take one scale. Suppose a simply supported, it's a rigid bar supported at two ends like this scale. Suppose this is supported here. Say simply supported. If I lift the end A through unit without disturbing end B, then whatever is the deflected shape is the ILD. That's all. Means introduce a unit displacement in the direction of structural function for which the ILD is to be plotted. Then without disturbing the compatibility or by maintaining the continuity of a structure, then the deflected shape of the structure itself is ILD. Means suppose, see this is AB, this is beam AB, and you want to construct ILD or RE. Then this reaction RA is to be removed. So it is supported at B. RA is removed and just lift this end through unit. So it becomes triangle. If this is the case, so and that plot the shape. If I lift RA through unit and plot the shape, so this is one. this is 1. And this is nothing but influence line diagram for RA. That means the ILD for RA or any structural function is obtained by removing the constraint offered by that function and introducing unit displacement in its own direction. Then the deflected shape of the structure represents ILD for that structural function. Very simple. Suppose if you want to draw ILD for RB, then just B is lifted off, keeping without disturbing support, left hand support, lifted up through 1, that becomes ILD for RB. If you want ILD for shear force at any section C, this is a simple, that's why I told that for simply supported beam, just keep in mind the nature of ILDs for shear force for simply supported beam, section within simply supported beam and section within cantilever beam. Now the left, we know this is left shearing. Once we cut here, the shearing should occur. The shearing should occur. So shearing means the shear force, we know that. So just like shearing, so left, down, right, up, and total shearing is 1. Means this is like this. So this is minus, this is plus. If this is A, this is B, this is A by L, B by L. But unit displacement means this total displacement is 1. Or see, in case of here, if this ordinate plus this ordinate, this is always 1. This ordinate plus this ordinate is always 1. Means it is the combination of ILD of RA and RB. So, but we have to draw ILD for RB on negative side and ILD for, if this ILD of RB, if we draw here on negative side, so this is the ILD for RA and this is 1, this is RB. And say RA is this. Then each and every ordinate of this represents shear force. So this total is 1. Everywhere if you take the total displacement, that is 1. So that C means, see, if you want here, say this diagram is to be removed. And this part of RB is to be removed. Because we know that depending upon position of unit load, when it is here, then RB represents shear force. When unit load is on this part, RA represents shear force. So ILD for shear force can be constructed even if we know the ILD for RA and RB. Or by sharing, allowing sharing at the section, we can construct. And in case of say bending moment, here the hinge is to be introduced and it is rotated, so just lifted up through unit. But remember, here this deflection is not needed. However, this rotation theta 1, theta 2, or say this is theta 1, theta 2. So theta 1 plus theta 2 is 1. So means give the unit displacement in the direction of structural function for which the ILD is required, then corresponding shape of structure represents influence line diagram for that structural function. Now let's define. So let's write down the definition for Muller-Bristol's principle. Now it states that if a unit displacement, if a unit displacement is introduced, in the direction of structural function, in the direction of structural function for which ILD is required. For which the ILD is required by removing restraint offered by that structural function. We will not write all these things. By for which the ILD is required, then the corresponding, in a simple way we will write down, then the corresponding deflected shape, of a structure represents ILD for that structural function, for that structural function or structural quantity, for that structural function. That's all. This is the statement. This is the Muller-Brussels principle. So it states that if a unit displacement is introduced in the direction of structural function for which the ILD is required, then the corresponding deflected shape of the structure represents ILD for that structural function. And there is a alternative definition also. If we obtain the deflected shape of the structure by introducing unit displacement in its own direction, then the deflected shape of structure is directly, or the influence line diagram is directly proportional to the deflected shape of the structure. So that is the alternate definition. Or I will write down the or. The ILD for any structural function or quantity such as reaction, shear force, bending moment. The ILD for any structural function or quantity is directly proportional to deflected shape of the structure, is directly proportional to the deflected shape of the structure, which is obtained by giving or introducing unit displacement in its own direction. So this is the alternate definition for Muller-Brussels principle. Now with the help of Muller-Brussels principle, how to construct influence line diagrams. Let's see the construction of influence line diagram. Again, we will see both this example, simply supported beam and the cantilever beam, because these are the important one in order to understand the influence line diagrams for compound beams. Say, let's consider the same example. Say we have a simply supported beam. Say take example A, B RA, RB, and here is the span, right? Say, now there is no need to show the moving unit load on the structure because we are not doing the calculations. So what Muller-Brussel's principle says that give the unit displacement in the direction of RA. So this keep end B simply supported, keep end B as a simply supported, just like this. One end, say this is A and this is B. So if you want RA, just lift through unit. B, don't disturb, B will be there only. So you will get a inclined line. So just like a triangle. So this shape itself is a ILD for RA. When you want to construct ILD for RB, so lift through one, so you will get ILD for RB. So just draw the shapes, deflected shapes. So RA means this RA is lifted up to unit, and this bar, assume that this is a rigid bar. So this end is lifted and draw a plotted shape. This is RA. So no calculations are required. Then lift B and B in the direction of RB through unit, and here it is 0. So this is RB. So no calculations. And even in exam, you use the Muller-Brussel's principle. Suppose your section AC is here, and this is distance A, this distance is B, and total span is L. Right? Now the section C, let's transfer here. SC, ILD for SC. And we know for simply supported, total sharing is 1. So left is downward, allow sharing, right is upward. So what we have done here, this should be linear, remember. This is linear. So this total sharing should be 1. This total sharing this is 1, this should be 1. And remember, this is minus, this is plus. Here this is plus, this is plus. So this is 1, here it is 1. So you get the ordinates at critical points even directly. So this, and now by using these two must be parallel to each other. This must be, only shear is to be released, not the bending moment. Means this line and this line is to be parallel to each other, and then you can find out this A by B, A by L, B by L, these ordinates by similar triangles. Then next, bending moment. Same, see in order here, release bending moment. So releasing of bending moment means what we have to do? So this supports are there. So we have to hinge, assume that the two bars are connected by hinge and they are allowed to rotate. Means they are allowed to rotate, bending moment is released, but not allowed to separate. Shear is not released. Only bending moment is released. So when we rotate, so it gets lifted off like this. So the ends here, they are connected by hinge, not separated. And this ordinate that we have to find out. How this ordinate is calculated? So this is calculated by using this. This angle and this angle is same, say theta 1, theta 1. This is say theta 2, theta 2. So we can find out theta 1 because we know this distance is A, this distance is B. So our now job is to find out H. So two relations we have, that theta 1 plus theta 2 equal to 1. Theta 1 plus theta 2 must be equal to 1. And again, this H A into theta 1 is equal to h.